This section is kind of a big deal. Here we're working with optimization problems, which, pardon the pun here, have very real world implications, because every single one of these problems that we're going to look at is a word problem. And what we're trying to do in these problems is we're trying to minimize or maximize some quantity. So let's say that I'm a business owner. I may want to maximize profits, or I might want to maximize revenue. I may want to minimize my costs, or I may want to minimize the amount of material used. So all of these have very practical applications. And this is one of the reasons why we care so much about calculus. This is kind of what these first 4 sections in Chapter 4 lead up to. So let's jump right in. I have a rancher that has 400 feet of fencing for constructing a rectangular corral. One side of the corral will be formed by a barn and requires no fence. 3 exterior fences and 2 interior fences will partition the corral into 3 rectangular regions. What are the dimensions of the corral that will maximize the enclosed area, and what is the area of that corral? Step 1, I think a lot of us could probably predict what it is. We want to draw a picture and use that picture to help us organize our information. So here I want to build a rectangular corral. And what do I know about this? Well, it tells me one side of the corral will be formed by a barn and requires no fence. So let's say this is the side that the barn is on. I don't need any fencing on this side because here's the barn. So okay, we're off to a good start. Let's see, 3 exterior fences. That's just saying here's 1, 2, 3 exterior fences. And 2 interior fences. This one we have to talk about a little bit more. 2 interior fences. Those are 2 fences on the inside of our corral. So we've got 1, 2 interior fences right here. We'll partition the corral into 3 rectangular regions. Partition just means it's a way to split something up. So I'm splitting this up into 1, 2, 3 regions right here. We would like to know what are the dimensions that will maximize the enclosed area, and then what is the maximum area. So we're looking for the dimensions. Let's label our dimensions here. I don't know the dimensions, so I'm going to call this side X. And if that side is X, then this side is also X. That also means that I need X feet of fencing for my 2 interior fences. This section at the bottom, though, that's not necessarily X. That might be a different length. It might be, say, Y units long. And as soon as you have your picture, you have a pretty good handle on what this problem looks like. You know kind of most of what the problem has given you. You're ready to move on to step 2. So step 2, we want to identify what's called your objective function. And this is a fancy way to say it's the function we're trying to minimize or maximize. So this is the function that we're trying to optimize here in this case. We would like to either minimize or maximize. Here in this case, we want to maximize the enclosed area, which means my objective function is going to be an area function. I want to maximize the area of this rectangular corral, right? So this region that I'm highlighting right now. Well, how would I find that area? It's just length times width, since it's a rectangle, so x times y. So this is the function that I want to minimize or maximize. But this looks a little bit different from a lot of the other functions that we've worked with so far because we've got 2 variables here. So we don't necessarily know how to optimize a function with 2 variables. So we need to see if we can simplify this function somehow, and that's what we're going to start to do in step 3. We're going to identify your constraints here. Now your constraints are some sort of limitation that we have. Because if I didn't have a limitation, I would just say, oh, well, go build a fence that's infinitely long and infinitely wide, and your fence will have infinite area, and there we go. But that's not particularly helpful because we can't build a fence that's infinitely long. In this case, we are constrained by the amount of fencing that we have. It says a rancher has 400 feet of fence for constructing this corral. We only have 400 feet of fence. So that means this side of my fence, and 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 this side of my fence cannot be more than 400. In other words, x plus x plus x plus x plus y, that cannot be more than 400. So I'm going to say that is less than or equal to 400. Now I could write it like this, but I'm going to assume that if we want to maximize the area, we want to use all of the fencing possible. So I'm just going to go ahead and say this is equal to 400. And of course we can simplify this a little bit. We can say, well, this is really just 4x plus y is equal to 400. So here's my constraint function. And okay, there's my constraint function. I want to use that now to help me simplify your objective function. So in step 4, I am going to say use constraints. You may have more than one, so I'll say constraints to simplify the objective function. So what I'm going to look at is I'm going to look at the constraint function that I have right here. I'm going to pick one of my two variables and solve for it. It doesn't really matter which one. We just need to solve for one of the variables. So I always say just pick whatever's easier. So I could take this equation and rewrite it as y equals 400 minus 4x if I just subtract 4x from both sides. And what I'm going to do is I'm going to take this constraint function now that I've solved for y with, I'm going to plug that into my objective function so that when I take out that y, I replace it with 400 minus 4x. So my area function here is area equals x, but then instead of y, I'm going to take out this y, and I'm going to replace it with 400 minus 4x. So x times 400 minus 4x. If we can, yes, we should probably simplify this. So this is really 400x minus 4x squared. So okay, there's my area function, and this looks a lot nicer to deal with because now we just have the one single variable. This looks a lot more like functions we've been dealing with in sections 4.1, 4.2, 4.3. And of course, we're not done yet. Step 5, we want to identify, and here let me change up the color here. I want to identify the interval of interest. So our objective function that we're trying to optimize currently right now is a equals 400x minus 4x squared. I want to identify the x values that make sense for our problem, because some x values, if we plug this in, we'll get like a negative area, and well, that doesn't make any sense. Area can only be positive. So we want to identify an interval that we're working on. Sometimes we'll just call this the domain of our function here. So one of our intervals here, one part of our interval, I should say, x, remember, let's go back and look. X represents a side length. X can't be negative. So that's another way to say, well, x should be greater than or equal to 0. So that's one part of my interval, what will be one part of my interval. The other one, I'm going to look at my other dimension here. Remember, y is also a side length. I'm also going to say, well, y can't be greater than or equal to 0, or excuse me, y has to be greater than or equal to 0 as well. But this isn't very helpful because I have x, I have y. I really would just prefer something in terms of x. So here I'm also going to take that constraint function that I wrote up here, and plug that in here as well. So 400 minus 4x is greater than or equal to 0. And I can solve this inequality relatively quickly. I should have negative 4x is greater than or equal to 400, which means x is less than or equal to 100. So that means x should be greater than 0, but less than 100. Essentially, we would like to be between 0 and 100. So our interval of interest, also known as our domain, is 0 to 100. This step might not seem important, but it really, really is, because this is going to help us identify what we need to do in our last step here. So identifying that domain is surprisingly important here. Because essentially what I'm trying to do in step 6 now, in step 6 we're going to, we've set this problem up. We want to find the absolute max or min on the interval that we just wrote. So I'm trying to maximize here. I want to maximize my area function, which is area equals 400x minus 4x squared on the closed interval 0 to 100. So here I'm working on a closed interval and I want to find the absolute maximum, which means that I need to do a couple things here. I need to find my critical points of my function that live within this interval, that live between 0 and 100. Once I have those, I can test that along with my two endpoints, because remember, we're working on a closed interval. Absolute extrema will either occur at the endpoints of our interval or at the critical point, so it's really important that we check them both. So okay, we should be able to start by finding our critical points here, which means I want to go and find a prime. So a prime, the derivative is 400 minus 8x. This is a polynomial. I really only need to worry about places where the derivative is equal to 0. So 400 minus 8x is equal to 0. We can solve this equation fairly quickly here. Negative 8x is equal to negative 400. Oops. So that means that x is equal to positive 50. So here's my critical point. I would like to test this critical point that I just found along with the two endpoints of my interval. I will plug those into my area function, into this area function right here, and then pick the absolute maximum because we want to maximize this function. So I'm going to start by looking at let's work with the endpoints just so that we don't forget to look at those. And let me change up my color here since we're doing something a little bit different. Let's start with 0 so that we don't forget to do our endpoints. I've got 400 times 0 minus 4 times 0 squared. Here we just end up with 0. Well, it's not a very good rectangle here. I might try plugging in 100 and say, well, area of 100, let's see, 400 times 100 minus 4 times 100 squared. We can go and calculate that, and we'll find, well, our area will once again be 0. So, okay, my last and only hope is this critical point right here. I need to take that as well. Area equals 50 equals 400 times 50 minus 4 times 50 squared. So let me grab my calculator here real quick. 400 times 50 minus 4 times 50 squared. Here I end up with 10,000. So I'm looking at these three y values. I'm trying to maximize this function. So I want, well, probably 10,000. I probably want an area of 10,000. It's just slightly larger than an area of 0. So we've identified our maximum. So the maximum area, let's actually just write some of this down before we lose it. The maximum area that we've identified is 10,000 square feet. What else were we asked to do? Let's go back and look at our problem here, make sure we answer it. So we found what is the area of the corral. That part's done. We would like to know what are the dimensions of the corral that will maximize the enclosed area. So we found the area. We said it was 10,000 square feet. Now we just need to find the dimensions. Well, one of the dimensions was, I'm going to highlight it right here, x equals 50. X equals 50 feet. That means I need to know, well, what is my other dimension? What was y? If you need to, refer back to your picture and say, okay, one of my dimensions was x. What was the other one? Well, it was y. So I want some sort of relationship between x and y. Perhaps I'll look at, I don't know, my constraint function right here. We said y is equal to 400 minus 4x. If I've identified what x is, I can just take that and plug that into this equation and solve for y pretty easily here. So y, let me just write this down before I forget. Y is equal to 400 minus 4x. So I want y is equal to 400 minus 4 times 50. And this will give me my y value. So if I do that, I should end up with 200 feet for y. So y will be 200 feet. So these are the dimensions that will maximize the area. 10,000 square feet, that is the maximum area. If you want to, you can also double check, take 200 times 50, I end up with 10,000. Everything seems good to go here. So there are a lot of steps with these problems, and we do want to take our time. I think that just once we get this problem set up and identify that interval of interest, then we're usually pretty good to go at that point. I think we're pretty comfortable with the back half of this problem once we've identified the objective function and simplified it and figured out our interval. But the real challenge of this section, I think, is just making sense of all of the information that's provided and getting to that point. So we're going to look at a few more examples here in the next few videos. And if you're still feeling uneasy at this, you may want to look up other examples. There's tons of videos out there for optimization that kind of walk you through some examples. You may find a YouTuber out there that you think does a better job of explaining it than I do, and that's perfectly fine. I'm sure there's plenty of people who explain it better than I do. But this is a tricky section. You'll want to look at lots of examples to really get a feel for how to set these problems up.